Previous lecture, we learned that a rigid body can have translation or pure rotation about a fixed point. And the third case, which happens a lot, is both of them together, general motion. So how do we formulate that? So here we assume this is a rigid body, and then we consider two arbitrary points, B and A. And the position vectors for B and A are R sub B, R sub A, and then the position of A with respect to B is R, A slash B. And pay attention that R slash B connects B to A. It's R of A as if the center is at B. So that is very important notation that we have to emphasize right here at the beginning. When we say R of B or A slash B, this is position vector of A with respect to B, i.e. it connects B to A, B considered like the origin and A considered like the desired point. Okay, so this guy connects B to A. This is very important. If you want the other way around, a vector that connects A to B like this green one is R of B slash A, while the red one is R of A with respect to B. Okay, so it's always the center is the point after the slash, and the end point is the point before the slash. That is the notation that we use a lot in this course. So clearly, using the triangular method for addition of vectors, I can say that R of A is R of B plus R of A with respect to B. And then I take a time derivative, and I get V of A is V of B plus V of A with respect to B, which is nothing new. We have seen this relative velocity formula in the past, but now the important thing is this relative velocity. So V of A with respect to B is the time derivative of this vector R of A with respect to B. But what's specific about R of A with respect to B? This vector, is there anything specific about it? And you might answer yes. The size of this vector, the magnitude of this vector is not going to change, right? Because it's the distance between 2 points on a rigid body, and we learned that it should not change. So this is a vector with fixed magnitude. So then does it have time derivative? Yes. Why does it have time derivative? Because it rotates, because the orientation of that does change as the rigid body rotates, right? So the rotation, the change in RAB with respect to time is not due to change in its magnitude, it is due to change in its orientation. Now, how can I calculate that? Well, there is a theorem in mathematics, in geometry, or in vector calculus, if you have taken that course, says, let me put that in a box for you. So this theorem says if A has a constant magnitude, or let's make it simpler, if magnitude of A is constant and A is attached to a frame or a coordinate system, doesn't matter, that rotates with angular velocity of omega with respect to a coordinate system, or let's say the coordinate system, XYZ, then, and here I can say frame, or instead of frame, let me use the word body, because in our case it's a body. Then we can show that d of the vector A with respect to time as measured in coordinate XYZ, let me use parentheses, it is equal to omega cross A. And proof of that is not really hard, but we try not to prove every single thing here. But if you want, please remind me in the class, and I can show you where this theorem comes from, but it should not be really hard to prove this. So if we have a vector with constant magnitude, and the only change in the vector is the orientation of it changes because it is attached to a body, to a frame that itself is rotating with respect to our reference coordinate system with angular velocity omega, then time derivative of that vector in this coordinate frame XYZ is omega cross A. And that's the same thing that happens here for this vector R of A with respect to B. This relative vector has a constant magnitude in this coordinate frame XYZ, and it is attached to a rigid body that the rigid body is rotating with angular velocity omega in general with respect to the frame. So d over dt of this vector, which is VAB, is omega of the rigid body cross R of A with respect to B. So I can replace this guy by omega cross R of A with respect to B, and this is valid when both points A and B belong to the same rigid body. Okay, so that is our big formula, that when A and B, okay, belong to the same rigid body rotating with omega with respect to, let's say, XYZ, then V of point A is equal to V of point B plus omega cross R of A with respect to B, okay? And this is the general velocity formula. This is our first big formula that we use over and over and over in this course for velocity analysis of rigid bodies. This is a super important formula, and we use this a lot. Now, does this formula just intuitively make sense? Well, I encourage you to look at two specific cases. One, if rigid body is translating only, so if rigid body has only translation, which means omega equals 0, right? When you have translation, you are not rotating. Omega is 0. What does it mean? It means V of A equals to what? V of B. Is that correct? Yes. We learned that's the definition of translation, that the velocity of any two arbitrary points is the same. Now, on the other hand, if the rigid body has pure rotation about B. So consider that point B is the center of rotation. If point B is the center of rotation, it means V of B is equal to 0. Then what would you get? You get V of A is equal omega cross R of A with respect to the center. Is that correct? Yes, this is the formula we just learned in the previous lecture, right? That V equals omega cross R, and R is the vector that connects the center of rotation to the current point. So you see, this general formula covers easily both of the two scenarios that we have seen so far, translation and pure rotation. But now, if B is not a fixed point and if the object is not in pure translation, then we have to add both of the effects together. In other words, this first component is the translation component, and the second one is the rotation component of A with respect to B. So when we add them, we're going to have both translation and rotation, and therefore we get this very important formula. Okay, now, what is the interpretation of this relative term omega cross R of V with respect to B? First of all, we know that cross product is always perpendicular to both original vectors. So I expect this relative term to be perpendicular to what? To R of A with respect to B. In other words, if this is the rigid body and this is R of A with respect to B, I always expect this relative velocity term to be perpendicular to that relative position vector, right? And the magnitude of it, if omega is perpendicular to R, not always that's the case, if omega is perpendicular to R, then it's the magnitude of first one, magnitude of second one. But in 2D cases, when life is quite simple, what we need to do is, when we want to basically visualize this equation, is this. If this is B, this is A, the object is rotating with this omega, then the relative term, we just learned that it is perpendicular to the radial vector. V of B is a component that is determined by point B, and then if I add these two vectors together, what do I get? I would get V of A, right? So what I can do is, at point A, look at this case, this example, this big figure is the best. At point A, what I do, I draw velocity of B. This is pure translation. Then, at the end of VB, I draw this vector of V of A with respect to B, which is what? Perpendicular to this line AB. And then the summation of the two is going to be what? V of A. Clearly, you see V of A and V of B, they do not need to have the same magnitude nor the same direction. So the only important thing is this, and I write it for you, that this term here, if I call this term, as we did, V of A with respect to B, the important point is this, that V of A with respect to B is always perpendicular to what? R of A with respect to B. It is always perpendicular to that radial vector. Okay, it is very important. Good. So now let's use this formula and solve a couple of examples here. So what we try to do is I would solve for you this first example of rolling disc, and then I would probably go over the slider crank mechanism, and then we'll leave this problem for the classroom. And then time allows, we start instantaneous center method, which is an alternative for this formula. So first, let's look at the nice problem, yet simple yet important problem of rolling without slipping. Remember when we did the this problem, we analyzed it a little bit before here in the classroom when we talked about this problem. In this case, we used the coordinate system at the center of the disk that was moving, and with respect to that, we found the velocity of the centroid, or the the contact point. Now we're going to fix this coordinate this time. So what we have is a fixed coordinate system, xy, and this disk is rolling without slipping. Without slipping means what? Means the contact point C has a momentarily zero velocity. It is stationary just at that moment that this picture is taken. And it is rolling to the left, and then what we want to find is basically velocity of the centroid, and maybe velocity of a point on the top, and so on and so forth. Okay? Or maybe a velocity of a point here on the left or right of the centroid. So what I would like to do with you, if you don't mind, I would like to take this picture again out of here and take it to OneNote, and then we analyze this problem together. So this is the problem of rolling without slipping. And again, without slipping means V of C is 0 at the moment, or momentarily. Just at that moment. Okay, so we can show it also. I can show you this, why it's 0. So another way to look at rolling without slipping is, let me get rid of this because we have to show it. Another way of rolling without slipping means if this disk keeps traveling, so let's say next time it is here, let's see if I can make it as big as this one. Yeah, it's not bad. So let's say next time it is here. Okay, and then let's say point B is here, centroid, and I call it point B prime, if you don't mind. And what happened to this point C? So point C, you know, when the disk rolls, point C comes to the right and upward. So let's say point C is here now. So if I could measure the angle of line BC with respect to a vertical line, okay, or the y-axis, the angle that you initially had with BC was 0 compared to the vertical line. Now, this is the line And this vertical direction, if I do it again here for you, this is the angle theta that the disk has rotated between these two positions, right? And now, let's say the radius of this disk is r. That's what we assumed. Now, this is my question for you. If I call now this new contact point D, or D prime, right? Can I ask you, what is the meaning of C prime, D prime? What is this guy? And D prime here was somewhere like this, maybe. So it was here in the first configuration, and now in the black, which is the second configuration, the point D, which was up here, now it came into contact and C went up, okay? So you clearly see this CD is now this C prime, D prime. So what is the length of C prime, D prime, or CD? What's this length? What's the length of this arc? What's the meaning of this? That is all of the points that came into contact when the disk moved from point 1 to point 2, right? So, and by the way, that is also the same as what? The distance between B to B prime, this distance, right? If I call it delta S of point B. Correct? This is the same as delta S of point B, and this is basically what? The distance traveled by the centroid of the disk. So this is the distance traveled by the disk. Good. Now, how can I find a relation for this? Well, we know C prime D prime is an arc. And the definition of angle theta, if you remember, if I want to describe angle theta in radians, the definition is what? Length of the arc in front of it divided by what? Radius of the circle. Therefore, I can say from these two that the distance traveled by the centroid of the disk is, if I cross multiply, it is going to be r times theta, and I guess everybody knows that. The distance traveled by the centroid of the disk is r times theta. Good. So now I want to take a time derivative from this. What is time derivative of distance traveled? It is velocity of point B, magnitude-wise. It is going to be what? R times theta dot. But what is theta dot? What is the time derivative of the angular displacement? Yes, that is omega. So this is the important thing. That when a disk rolls without slipping, the magnitude of velocity of the centroid is r times omega. Fine. Now, I want to use this formula that we just learned and apply it instead of between A and B. Here, I want to apply it between C and B. So I want to write V of C, the contact point, is equal to V of B plus omega cross R of C with respect to B. Yes, I applied the generalized formula. Now, let's use this and write everything in vector notation, see what we get. What is V of B? This is its magnitude. Which direction is V of B? The centroid itself. Clearly, it is moving to the left. And here, x is to the right, positive. So, this is the magnitude. The direction is negative I. So, I can write this as what? Negative R omega times I, right? Magnitude times unit vector, negative I. What is vector omega? Vector omega is counterclockwise, and we learned that when x is like that and y is like that, and then z-axis is out of the plane, counterclockwise means positive z or positive k. So I can write it as positive omega times k, right? Magnitude times direction. And what is r of c with respect to b? Remember, c with respect to b means it connects b to c. So it's this vector. What is this vector? It is r units in magnitude, and it is downward, so it's negative j. So I can write it as what? Negative r times j, if you don't mind. And now what would you get? You're going to get negative r omega I, and then what is this one? It's going to be negative r omega k cross j, and if you know, k cross j is what? It's negative I. But you have another negative, so you're going to get what? Positive I. So you're going to get this one, and you add them together, you're going to get what? 0. So we got back to what we wanted. Right? That V of the contact point is 0. That's another way to describe rolling without slipping. That's the meaning. Slipping means which point slips? The contact point. If it doesn't slip, if it doesn't move horizontally, then the velocity of the contact point is what? 0. So that's another way to talk about rolling without. In rolling with slipping, then V of C is clearly not equal to 0. So this is rolling without slipping. Now, before I go forward and talk about velocity of other points on this disk, I want to talk about this slipping. So if rolling happens with slipping, what's the difference? Clearly, you can show that V of C is not equal to 0 in magnitude, or vector, doesn't matter. Not only that, you can also show that V of B, and I leave that up to you to show, V of B, magnitude of it, is less than R omega. Okay, so if they are equal, it's rolling without the slipping. If VB is less than R omega, it means there is a slipping. Just I give you an example so that you can digest this a little better. Assume that your tire or your disc is on the ice and it is just spinning in place, right? If you are spinning in place and just doing pure slip, what happens? Since you are just moving in place, just rotating in place, spinning in place, V of centroid is 0 because it doesn't move. But is your R omega 0? No, because you are clearly spinning. So the max difference is when you are spinning in place. This is 0, this is non-zero. The more VB comes close to R omega, the less slipping you have until they are perfectly equal, and then the slipping is going to be 0. Okay, so this is rolling with or without slipping. Now, what if you want to find velocity of other points on this disk? Right, so this is your disk, and you want to find velocities of some other points. So here, I will do it myself. So this is one point, this is another point, this is the disk, right? And then this is the contact point, this is the centroid, this is a point right on the top, and maybe this is here, a point behind the centroid. This is going with omega, and the radius is r, and this is x, and this is y, and z is out of the plane. So what if I ask you now, so we found that v of c is 0, fine. Now what if I ask you what is v of a and what is v of d? And let's just add v of b as well to this, if you don't mind, for the sake of completeness. So what is v of b? We found that it's negative r omega I. What is v of c? We found that it's 0. What is v of a? What is v of d? So just to practice this formula more, we want to calculate the velocity of 2 more points. Let's start with a. What is v of a? So we write this formula that v of a is v of b plus omega cross r of a with respect to b, and v of b, I have it, it's negative r omega I. Omega was omega k, positive omega k, and r of a with respect to b is this vector, which is positive rg. So this time you're going to get positive r omega k cross j, which is negative. So you're going to get negative r omega I, negative r omega I, you're going to get negative 2 r omega I. Which is what? 2 times velocity of b. So this is negative 2 r omega I. So if this point is moving with velocity b forward, or the magnitude of it is r omega, this point is moving with what? Negative 2 r omega I. And this point here, c, does move with 0 velocity. So if I connect a to c, and then if I connect the end of velocity of c, which is 0, to r omega I to 2 r omega I would get a what? I would get a linear profile. And I can show that, for example, if this distance here is, if I consider a point here, which is halfway between c and b, the velocity of that is 1/2 of r omega I. If I consider a point between a and b, then the velocity of that is 3/2 r omega I. So the linear profile does exist here between a to c. Now what about point D? D is also interesting. So point D, velocity of it is equal to v of b plus omega cross r of d with respect to b, and r of d with respect to b is this guy. Negative ri. So you're going to get negative r omega I. This is omega k, and this is negative ri. And here you have k cross I, which is j, but you have a negative here. So it's going to be negative r omega I, negative r omega j. So if you want to show it here, it is going to be the same magnitude as v of b forward, and then the same magnitude downward. So it looks like this, basically. Let's just make sure. I guess the j should be positive. Make sure I'm not making a mistake. It's k cross I, right? Yeah, it is negative j, and with that it's going to be positive j. Yeah, I made a mistake. This is positive j. So the velocity of d, it will look like this. Okay? Which, if you want, it is perpendicular to this connecting line from C to D. Okay, so this guy is negative r omega I, plus r omega g, and so on and so forth. So this is an interesting example. Then we have two more problems. One of them we're going to look right now, example 17.2, and then problem 1756 we are going to do inside class. Although actually this problem is quite easier than this one, but I would rather solve this one right now. So let's get to this problem. Okay, so in this example 17.2, we are talking about the slider crank mechanism, which is the mechanism that you see in car engine with crankshaft, conrod, and piston. So this member AB is called crank, the member that basically rotates fully. And then your piston is called slider because it slides inside the cylinder. This is a simplified model of this slider crank mechanism on the left. Okay, and here we have some numbers. These numbers not necessarily match the actual dimensions, but this is just a simplified version of this mechanism. So the length that you see here, 0.4, 0.4, and 0.8, again, might not exactly match, and they will not exactly match mostly the actual length. And here, what we want to know is if the crank bar AB is rotating clockwise with 10 radians per second as shown, you find the velocity of point C and then the angular velocity of the conrod omega BC. Okay, so we're going to take this guy and we're going to go here and solve. So here we set up our coordinate system as we usually do, right? So this is our XY coordinate, and we know that Z is out of the plane, of course. So whenever we are given a mechanism and more than one rigid body where they are connected together like this, so BC and AB are connected at point B, what we do, so here omega AB is given, right? You know omega AB is 10 radians per second clockwise. You want to know how much is omega BC, magnitude and direction, and then how much is V of C, again magnitude and in which direction does C go. So when you work on this, what you would do is you start from the points, or not point, the rigid body that you know something about, and move towards those rigid bodies you don't know anything about. So here you have two rigid bodies, AB and BC, and in AB you know something, you know omega. So I would write my formula, this important formula that we learned, I write it where? For object AB. And then here in object AB, you need 2 points to relate their velocities together. Which 2 points do you choose? Your candidate points are either the points that you know something about their velocity, or the points that are also, they do also belong to other rigid objects. They are common points, they are intersection points. So B is a good point because you can find something about it from AB and find something about it from BC. That's a good candidate point. And A is a good point because it's a pivot point and velocity of it is 0. So what I would do, I would relate here V of B to V of A by the general velocity formula that I just learned. V of B is V of A plus omega object AB cross R of B, with respect to A, and that vector is this guy here. R of B centered at A or with respect to A. Okay, what do I know now? V of A is clearly 0, it's a pivot point. Omega AB is 10, but it is clockwise, and since Z here is out of the board, clockwise is in the board, so this is going to be negative 10 times K. Is in the negative K direction. R of B with respect to A, you see, is 0.4 units forward and 0.4 units upward. So this is going to be 0.4I plus 0.4J. And so if you simplify it, what would you get? You get K cross I, and you know K cross I is negative J, or positive J, K cross I is positive J, but there is a negative here. So it's going to be negative 10 times 0.4, which is 4. So negative 4J, and then K cross J is negative I, but you have a negative, so it's going to be positive. So you're going to get 4I minus 4J. Units, meters per second. This is V of B. Does it make sense? Always take a look, do the sanity check. So it says V of B should be forward, positive I, but negative J, downward. So V of B should be something like this. Right? Positive I, negative J, which by the way should be perpendicular to this line since it is rotating about a fixed point. So it says V of B looks like this. Does that make sense? Negative J, positive I? Absolutely. So it is fine. Now you go from object AB to object BC. Again, which 2 points to use? Clearly point B, because now you know its entire velocity. And C, first of all, not only it's one of the interest points, we know something specific about point C. We know C only moves horizontally. We don't know how fast, but it is in the on the x-axis. So now I say V of C is equal to V of B plus omega BC cross R of C with respect to B. And now V of B, I just found it, so I replace it for I minus 4J. Omega BC, what is that? I don't know. That's one of the unknowns of the problem, right? That's one of the unknowns here. But this object BC has to either, because this is a 2D problem, this object BC has to either go clockwise or counterclockwise. There is no other situation. So it's either positive K or negative K. So for the moment, I assume that it is positive K. Does it necessarily, is it necessarily correct? Maybe not. So what happens if it's actually negative K? If it's really clockwise, what would happen? No problem. When you solve this for omega BC, and I'll show you how, when you solve, if the initial direction that we assumed is wrong, the number that you will find for omega BC will turn out to be what? Negative. So as long as you got the line of action correct, the direction, if you initially assume it wrong, the solution will correct you. Okay, you'll see the solution would give you a negative number. What is R of C with respect to B? That is this vector. It should connect C with respect to B, so it connects B to C. And what is this vector here? It is point I, 0.8 unit forward in the I direction, and 0.4 units down, right? So minus 0.4 G. What about VC itself? Do I know anything about C? Well, what I know about C is C, as I said, should only move what? on the x-axis, right? So it is either positive I or what? Negative I, right? Which one? I don't know. Here, I consider it to be positive. So I say it's positive VC times I. Again, if it was really moving to the left, what happened? You end up with a negative number. If you want, let's practice that. So here, let's do that. Let's say I say it is moving to the left, so it is negative VCI. Okay, fine. So I know it's wrong, but I deliberately consider it wrong, and we're gonna see what we end up with these two unknowns. So now, this is my equation. I have two unknowns in this equation, VC and omega VC. Both of them are unknown. Well, can I solve for both unknowns from one equation? No, but the problem is this is not one equation. This is actually two, because this is a vector equation, right? And a vector equation is valid when the I components of the left and right are equal and the J components. So first thing, let's do this. I simplify this for you, so it's going to be 4i minus 4j, this first one, and now I carry the cross product, so it's going to be k cross I, right, which is j, so it is going to be 0.8 omega bc j, and then this is minus k cross j, which is negative I with negative positive I, so you're going to get 0.4 omega bci. So now this vector on the left is equal to this vector on the right. And we know from vector calculus or vectors that two vectors are equal if and only if what? Their I components are equal and their J components are equal. So what do we have for coefficients of I here? How many I's do you have on the left side? Negative VC I's. How many I's do you have on the right? You have a 4 here and you have this one here. So it is going to be 4 plus 0.4 omega bc. On the other hand, how many J's do you have on the left? None. There is no J. This is plus 0 times J. So I only have 0 J's on the left. On the right, I have what? I have negative 4 and then positive 0.8 omega bc. So from the bottom one, I can solve for omega bc. It is going to be 4 divided by 0.8, which is 5, and it is going to be positive. Positive means what? Look, I assumed it to be positive, and it turned out to be positive. So my initial direction that I consider positive, positive means what? It means counterclockwise. The direction that I consider counterclockwise was actually correct. Fine. Now I plug this back into the top equation, and I solve for V of C. You're going to get 2 plus 4, 6, but there is a negative. You're going to get negative 6 meters per second. Now, what does it mean? I assumed it to be negative. But now the answer I found for VC is negative. Negative means whatever direction you initially assumed is not correct. You should invert it. So I consider it to be to the left, but this one tells me no. Actually, it's this negative 6 times negative I, so it is what? It is positive 6. So the actual direction of motion for point C is to the right. Okay? Well, if I initially said that, no, I think point C is moving to the right, and I did this positive, then this one would be positive, this one would be positive. So you end up with a positive number because initially your assumption was right, and still this and that means it is to the right. So it doesn't matter when you started wrong or right. The solution, the sign of the solution would tell you whether you started right or wrong. Okay, so this is how you solve this problem. So what really matters here for VC and omega BC is their line of action. This is a line K, this is a line I. Positive or negative? We'll find out at the end. Just go with one assumption here. So here we assumed something, and here we assumed something. And go forward, and then the sign of the solution will tell you whether your assumption was correct or not.